Good afternoon, good evening, good morning. I'm Minju Lee, and I'm currently working as a postdoc at MP, and will be moving to Dawn. I didn't know that Sean will also move to Dawn, and thanks. Nice to meet you for the future collaboration. So anyway, so first of all, I would like to thank again for the organizers for this nice conference. I'm learning a lot and giving me the opportunity to give a presentation. So the topic that I will give today is regarding the gas mass calibration in a Redshift 2.5 protocluster using atomic carbon, CO, and dust. Previous talk already showed a similar figure, but I just wanted to give a brief introduction. So over the past 10 years, we have seen a great improvement in understanding of gas content for high redshift galaxies, especially for redshift above 1. Probing gas content gives an idea of how stars formed in galaxies and how efficient it was. For field galaxies, it generally follows the trend of the cosmic star formation rate density, which peaks at around 1.5. But this figure, in fact, doesn't ever averages out all the information relevant to the large scale structure. So it is very difficult to infer how the galaxy formation and evolution changes as a function of environment. So this is why many people are trying to measure the gas content in different environments, including protoclusters, clusters, and voids, and so on. So actually, this is my second attendance in GCF conference. I gave a talk in 2017, and I showed that our results from protocluster redshift 2.5 using CO322 and dust, which gives a consistent gas fraction for the main sequence galaxy. But of course, there was a tension between CO-based and dust-based measurement for a subsample of galaxies. Also, there was a hint of a larger scatter in terms of the gas fraction. While we reported the non-insignificant difference compared to field galaxies, other different groups also reported a contradictory results, like higher gas fraction, lower gas fraction. So the field is something like this. We are having a different results from different groups. So, but one question came to my mind before discussing any differences in different environments at various redshift from a statistically meaningful sample, shouldn't we better to check again the gas measurements from different gas tracers? That's my simple-minded motivation. So the background is that protocluster galaxies might have different gas conditions, ambient radiation field, metallicity, and so on, compared to the galaxies at similar redshift. So are we really sure about the using the same gas recipe for the protocluster galaxies? So this is the answer that I would like to test. For galaxies well above the main sequence, which is often located in protoclusters, it is quite obvious to use the Euler starburst convergence, but for the main sequence galaxies, it's less obvious. Observationally, to trace the molecular gas, often CO and dust are used because the most abundant species of molecular hydrogen cannot emit in a typical condition of ISM, which doesn't have a permanent dipole moment. So for CO, if you want to use ALMA or NOEMA, whatever you like, the lowest transition of CO1 to 0 is not available. So you need to assume additional assumption of the gas CO excitation. You could also use for the lowest CO transition, as previous talk said, JVLA at can target, but it seems that it is quite expensive, especially for the galaxies at the peak of the galaxy formation. Dust, obviously efficient, but it is not well calibrated for high redshift galaxies, especially for above redshift 3. It includes uncertainties of dust temperature, gas to dust mass ratio. So I thought that one might need an additional good tracers to cross-calibrate the gas mass. So I learned from a local study that the CO1 to 0 and C11 to 0 shows a very tight correlation, almost 1-to-1. So C1 can be a very good cold gas tracer. It is very optically thin tracer compared to CO. So it is also a good thing to use. For high redshift galaxies, C1 is compared to C1, a CO less affected by the cosmic ray, metallicity, and cosmic microwave background. Of course, it is another tracer for molecular hydrogen, where there is uncertainty of the C1 over H abundance ratio. So I add C1, 1 to 0, and try to get a self-consistent gas mass. So here comes the new observational study for the same protocluster. If I briefly introduce about this protocluster, it is less famous than the spiderweb. It is at redshift 2.5, and it is an overdensity region close to a radio galaxy here. It has known to have abundant overdensities of galaxies differently selected in different methods, including H-alpha emitters, submillimeter bright galaxies, and IRAC galaxies as well. With the improved specs information, of course, many cluster people will argue that this is like trash for measuring the halo mass. But if we try to best guess for the halo mass of this system, it is roughly 10 to the 13th solar mass, and it is likely a present-day Virgo-like cluster progenitor. I will be mostly focusing on the massive end H-alpha emitters, main sequence galaxies, which have a relatively secure constraint of the stellar mass and the star formation rate. We targeted this field with 2 pointings with ALMA, and we detected 5 galaxies of C1, 1 to 0, CO4 to 3 on top of CO3 to 2, and thus continue, which allows a comprehensive analysis of individual galaxies. So our hypothesis is check whether the recipe applied in field galaxies can be applied in protocluster galaxies. So we use the exact same recipe applied for the main sequence galaxies, and here's the result. On the vertical axis, we show the CO and dust-based measurement on the vertical axis, and horizontal axis is the C1 based measurement. So the dashed line is the one-to-one relation. So in general, they are broadly consistent with each other. But if you take a closer look, dust and C1 is more consistent with respect to the CO. So difference can be up to 0.4 dex between CO and the other tracers. We have explored the potential variation in assumptions of different tracers, but our final conclusion is that the molecular gas from CO may have been overestimated, suggesting that lower alpha CO and starburst like CO SLAT might be needed for some galaxies. So given that we are relatively confident on the gas measurement for this star-forming main sequence galaxies using C1, we drive the gas fraction again, and it gives, we confirm the measurement in the previous observation, giving 0.5, which is consistent with the field galaxies. But there is we find a different level in terms of the depletion time scale. So on the right panel, it shows the depletion time scale normalized by what is expected from the field galaxies. So there, of course, there is still a narrower range in terms of the gas stellar mass or depletion time scale, but we find a different level of stellar mass dependency for the depletion time scale. So it might be relevant to, so if you go to higher stellar mass, depletion time scale is shorter, meaning that it may be quenched earlier. We could try this trend. The formation of the more dense gas expected, after we explore the CO4 to 3 and CO1 to 0 ratio, it seems that some galaxies have a denser gas, like above 10 to the 4 cubic centimeter per cubic centimeter. The formation of the denser gas may be related to frequent mergers, because we found that from the literature value, by gathering all the available CO line widths, in protocluster, we find 50% wider CO line widths for the galaxies. So it may be relevant to the unresolved mergers, but also it can be explained by the smaller size at fixed dynamical mass. Okay, I'm almost done. But there is another possibility. Gas dripping. We expect that one galaxy might be seems to show this kind of signature with the extended H-alpha emission. But of course, given that the high gas friction, comparable to field galaxies, this instability, like in situ galaxy formation, can happen. There are other possibilities. So anyway, what I want to do here is that all possibilities are considered and it can be possible. I cannot reject any of the possibilities. So more sample is needed. So finally, this brings me to the final last 2 slides for introduction of the ongoing effort to use ALMA archive. So I'm trying to improve the statistics by using dust continuum, because the learnings from the previous study is that dust seems to be really efficient and seems to be quite a good gas tracer to measure the gas content of the galaxies in different environments. So I'm currently exploring ALMA archive. So currently above 100 public ALMA programs corresponds to roughly 200-hour equivalent on-source time has been explored. And I hope that I can present the results in the next 3rd GCF meeting. Yeah. So this is my summary. We confirmed the gas fraction of 1.5 on average, being consistent with the field, but a stronger mass dependency in depletion time scale, which may be relevant to the earlier quenching in this environment. But there are many possible mechanisms that we can consider. So more data and in different environments may be still needed. And I also wanted to argue that C1 can be a good cold gas tracer for high redshift galaxies, even in dense environments. So please consider if you want to propose for ALMA, for example. Yeah, so that's all that I prepared, and thank you.